In the last video, I have discussed what is Born-Haber cycle, the origin of Born-Haber cycle, construction of the cycle, how thermodynamic parameters are involved in it, how lattice energy can be experimentally estimated using Born-Haber cycle. In this current video, I will show few interesting applications of Born-Haber cycle such as stability of ionic lattice or lattice of some inert elements, calculation of proton affinity, suitable formula of ionic compounds, etc. using the concept of Born-Haber cycle, which I have already discussed in my previous video, whose link is provided in the description box. Now some applications and significance of Born-Haber cycle. Number 1, lattice energy of different ionic lattice which are calculated from this Born-Haber cycle, that means experimental way where different thermodynamical steps or parameters or energy terms are involved. That lattice energy values are well correlated with the lattice energy is calculated from different theoretical methods like Born-Landy equation or other equations. Here some lattice energy value of different ionic lattice and their calculated value as well as lattice energy value coming from Born-Landy equation are compared in a tabular form, where we can see for alkali metal halides like lithium fluoride, lithium iodide, sodium fluoride, sodium bromide, sodium iodide, cesium fluoride, cesium iodide. For these lattices, the calculated value as well as the lattice energy coming from Born-Haber cycle, that means experimental value, are well correlated, as we can see here. For lithium fluoride is 1029 kilojoule mole inverse, and for Born-Haber cycle it is 1035, almost equal. For lithium iodide it is also 730 and 757, something different. Sodium, in the case of sodium fluoride, it is 915 and 914, almost same. Sodium bromide also 739 and 728, almost same. But in the case of transition metal halides like copper chloride, we can see the calculated value is 904, but in the case of Born-Haber cycle it is 993, a huge difference. In the case of silver fluoride it is 920 in the case of Born-Landy equation, but for Born-Haber cycle it is 953. It is also far different. As well as silver chloride, the calculated value of lattice energy is nothing but 832 kJ mole inverse, but from Born-Haber cycle it is 903 kJ mole inverse, a huge gap. Why it is so? Actually, for these cases, transition metal halides, due to presence of transition metal where incompletely filled or d orbitals are there whose shielding effect is very poor, as we know, and hence a huge nuclear charge or Z effective is filled by the valence shell or other atom coming from outside. So the size as well as the ionic potential are changes in these cases. That is why the calculated value is not correlated with the Born-Haber cycle in very good agreement. Many other example we can see this type of different lattice energy in calculated value as well as lattice energy coming from Born-Haber cycle are well correlated for alkali metals, especially alkali metal halides, but it get differed in the case of transition metal halides. We can see many other examples. Now, application number 2, from Born-Haber cycle of particular lattice, we can predict the stability or instability or amount of stability of a particular lattice by comparing the thermodynamical term, different thermodynamical term involved in the Born-Haber cycle. That means stability of the particular lattice and some thermodynamical terms related or provoke the stability or increase or decrease the stability of the lattice, we can predict or we can comment from Born-Haber cycle. Now let us see few terms involved in Born-Haber cycle like delta H sublimation, ionization energy, dissociation energy, bond dissociation energy, delta H atomization, delta H vaporization. This type of energies, this type of terms are nothing but thermodynamically positive term. That means where we have to supply some energy to the system to perform the work. So these terms are nothing but our related to instability of the lattice. Here energy loss taking place. But other few terms like delta H formation, electron affinity and especially lattice energy term are thermodynamically negative term. That means these energies are released or removed or emitted from the lattice when it forms or when the compound is formed. So higher is the value of these terms, that means especially formation energy or lattice energy. That means when this lattice is formed, then large amount of energy is released, and that is why that lattice become very stable. So higher is the lattice energy, especially lattice energy, higher will be the stability of that lattice. So generally high charge species, that means higher cationic charge species or higher anionic charge species, are generally form lattice having high lattice energy. That means generally stable lattice. Now here I have chosen 4 examples of different type of lattice, and its corresponding lattice energy are shown here in kJ mole inverse unit. As we can see, for magnesium oxide, here magnesium 2 plus in gaseous ion, oxide 2 minus in gaseous ion, producing magnesium oxide solid lattice, and whose lattice energy is nothing but very high, minus 3800 kJ mole inverse at 298 K. For tin oxide, here also tin 4 plus gaseous ion combined with 2 oxides gaseous ion to produce SNO2 solid, whose lattice enthalpy nothing but minus 11595 kJ mole inverse. As well as for magnesium fluoride, it is also minus 2923 kJ mole inverse. So first three example where we can see very high lattice energy, and that is why this type of lattices, magnesium oxide, tin oxide or magnesium fluoride, are very stable in nature due to this high lattice energy value. But as we compare with sodium chloride NaCl, where Na plus solid and Cl minus, Na plus solid become Na plus gas and Cl minus gas will produce NaCl solid, whose lattice enthalpy is nothing but minus 760 kJ mole inverse, which is very lower than that of the previous three. So comparing this lattice energy with others, we can say sodium chloride lattice is less stable than that of magnesium oxide or tin dioxide or magnesium fluoride, as its lattice energy is very poor than that of previous three. Again, for stability of the lattice and relation with Born-Haber cycle, one interesting question or one interesting finding is that check whether ArCl, argon chloride solid lattice, exists or not. The other supporting data are given here. Ionization energy of air gas is nothing but this value, very high, kJ mole inverse. Dissociation energy of chlorine is that, electron affinity of chlorine, as well as lattice energy of ArCl solid is given. So we can easily comment whether ArCl solid or lattice is formed or not, or stable or not, or exist or not from Born-Haber cycle. So at first we have to construct the Born-Haber cycle of ArCl. So I have already constructed it. Air gas to air plus gas, ionization energy, only one step, and as previous Cl minus gas to half dissociation energy is required for one atom chlorine gas producing process, and then chlorine gas to Cl minus ion, that means electron affinity, and combining these two, Ar plus and Cl minus, producing ArCl solid. It's the term involved is nothing but lattice energy. And here in the left side, argon gas and chlorine gas directly heated to combine each other to form ArCl solid, and the energy involved in this term is nothing but the formation energy. And using Hess's law, we can easily calculate or measure the formation energy using this equation. And we find that after putting this value in this equation, the formation energy of ArCl solid is nothing but highly positive, plus 595.5 kJ mole inverse. So we know very well that in thermodynamic view, when a particular lattice or compound is formed, higher is the negative value of formation energy in terms of thermodynamics, higher will be the stability, or that compound must be exist. But if the formation energy is positive, then that compound or that lattice must be very unstable or does not exist. So here our hypothetical argon chloride solid lattice does not exist, since its formation energy value is highly positive, and we can calculate this value from this Born-Haber cycle data. So from Born-Haber cycle we can predict whether any particular lattice or solid exists or stable or not. Now application number 3, electron affinity value of some element can be calculated or estimated from this Born-Haber cycle of that particular lattice. Some electron affinity value of some element, it is very difficult to estimate or calculate from different thermodynamical process. So for that cases we can easily estimate or calculate or easily find the electron affinity value using Born-Haber cycle, putting the other term involved in this cycle, as we previously done for magnesium sulfide lattice. We calculate the EA value for this step. Previously we have done using the Born-Haber cycle of magnesium sulfide. Again, for sodium iodide lattice, here also we can calculate or estimate the EA for iodine gas. For this equation, I gas plus electron I minus gas. For this reaction or this step, EA can be calculated for iodine using Born-Haber cycle of sodium iodide. We can easily calculate. Again, here another problem where using Born-Haber cycle calculate electron affinity of hydrogen. It is also difficult to predict or calculate in kJ mole inverse, given other supporting parameters like delta H formation of KH potassium hydride solid and sublimation of potassium, ionization energy of potassium, bond dissociation energy of hydrogen, and lattice enthalpy of potassium hydride solid. So here also the formation of hydride, that means hydrogen gas accepting one electron in its valence shell from outside, producing hydride gas. This step, the energy involved, you have to calculate. The electron affinity of hydride is not estimated very easily. So, but using this Born-Haber cycle, we can easily estimate or find the electron affinity value of hydrogen to hydride in this step. And this is one of the very interesting application of Born-Haber cycle. Now application 4 is nothing but the formula of ionic lattice can be justified using Born-Haber cycle. So let us consider one ionic lattice like sodium chloride, very common, is called common salt. So what is the formula of sodium chloride? Whether it is NaCl or it is NaCl2. So we have to justify which formula is correct using Born-Haber cycle. Here some supporting data are given, like sublimation energy of sodium solid, first ionization energy of sodium gas, second ionization energy of sodium plus gas, and bond dissociation energy of chlorine, electron affinity of chlorine, lattice enthalpy of sodium chloride NaCl2 solid, as well as the formation energy of NaCl. So now, using this data, we have to construct at first the Born-Haber cycle of NaCl2. So I have constructed the Born-Haber cycle of NaCl2 where these terms or these thermodynamical terms are involved. Here sodium solid to sodium gas, delta is sublimation, then Na plus, Na2 plus, ionization energy 1, ionization energy 2, then chlorine to chlorine gas molecule to chlorine atom in gaseous state where bond dissociation energy, full bond dissociation energy required here. Then 2 chlorine to 2 Cl minus, that means 2 electron affinity is required. Then combining this Na2 plus and 2 Cl minus in gaseous state, producing NaCl2 solid, and the term involved is nothing but lattice enthalpy of sodium NaCl2 solid. And here also in the left side we directly combine with sodium gas, sodium solid and chlorine gas to produce NaCl2 solid. Then the term involved, the corresponding term involved is nothing but the formation energy of NaCl2. And using Hess's law, we have written the Hess's law. The formation energy of NaCl2 solid is equal to sublimation energy, ionization energy 1, ionization energy 2, bond dissociation energy, 2 electron affinity, and lattice enthalpy of NaCl2. And putting all these numerical terms in this equation, we can calculate the formation energy of NaCl2, and it is nothing but a very high positive value, 2560 kJ mole inverse, very high positive value. But as we know, formation energy positive means highly unstable lattice. Lattice does not exist actually. Here is the positive energy of formation energy. The lattice must be unstable. And comparing this value with the formation energy of NaCl here, this is the formation energy of NaCl. It is nothing but minus 381 kJ mole inverse. And for NaCl2 it is nothing but plus 2560, very high positive. So we can comment or we can say that from this thermodynamical cycle or Born-Haber cycle, NaCl2 does not exist, and the formula, actual formula of sodium chloride is nothing but NaCl but not NaCl2. As previous, we can predict the or find the formula of calcium fluoride, whether it is CaF or it is CaF2. So that is why we have to construct a Born-Haber cycle of CaF at first, and putting all these data in that Born-Haber cycle His law to find the formation energy of CaF. So at first I try to construct the Born-Haber cycle of CaF. So Ca solid to Ca gas. This step is nothing but delta H sublimation. Here Ca plus unipositive ion in gaseous state, that is nothing but ionization energy 1. Now F2 gas to 2F, sorry, only F gas, so half D is required. Now from F gas to F minus gas, so here electron affinity of fluorine is required. Now here we combine calcium plus and fluorine minus in gaseous state to form CaF solid lattice, where the energy term involved is nothing but lattice energy. And here at the left hand side we directly combine calcium solid and fluorine gas to produce CaF solid. Here the enthalpy term involved is nothing but delta H formation of CaF. Now applying Hess's law, we can write delta H formation of CaF solid is nothing but all other term involved in this equation, that is delta H sublimation plus ionization energy 1 plus half D plus Ea electron affinity of fluorine plus lattice enthalpy. Now putting these thermodynamical values, energy values from the above data like this, 201 plus 590 plus half 159 plus electron affinity means minus 335 and lattice enthalpy minus 795. Delta H formation of CaF solid is equal to minus 259.5 kJ mole inverse. Here also put kJ mole inverse. So we can see the delta H formation value of calcium fluoride. Calcium fluoride is nothing but minus 259.5. It is minus, hence it should be stable. So calcium fluoride CaF, whose formula is CaF, is stable since its delta H formation is negative energy, but this value is very small. It is nothing but minus 259.5 kJ mole inverse, whereas in the case of CaF2 the delta H formation value is nothing but minus 1243 kJ mole inverse. Very high negative value. So this lattice is highly stable compared to that of CaF2. That is why when anybody try to produce CaF applying this Born-Haber cycle, and when CaF produce, since its formation energy very lower than that of CaF2, so this CaF is converted to CaF2, or we can say CaF is disproportionate to CaF2 and metallic calcium as shown here. CaF to CaF to CaF2 plus metallic calcium, where this is plus 1, this is plus 2 and 0. So plus 1 calcium is disproportionate to plus 2 higher oxidation state and 0, that means lower oxidation state. Since its formation energy value is much lower than that of CaF2, which is very higher formation energy, and hence this compound is highly stable. So the actual formula of calcium fluoride is nothing but CaF2 but not CaF. Now application number 5. Another important and interesting term, proton affinity, PA. This term is actually related to the gas phase acid base reaction, where the components or reactants are both in gaseous phase. That means proton also in gaseous phase, and other species which accept proton, that is called base, is also in gaseous phase. So we can explain it in terms of this equation, like any substance in gaseous phase which accept a proton which is also in gaseous phase, combining in this acid base product. So in gas phase both this reactant react and proton is accepted by A. And in this reaction the amount of energy released due to formation of this adduct, it is called proton affinity. So proton affinity is highly related to gas phase acid base reaction. So we can comment or compare the basicity or in gas phase basicity of any molecules, atoms, ionic species using this proton affinity term. That means higher is the value of proton affinity of this type of reaction, higher will be the basicity of the substance or molecules or atoms. Now correlating with this Born-Haber cycle, we can calculate or experimentally calculate proton affinity using Born-Haber cycle. Since proton affinity value of this type of reaction is very difficult to estimate. So we can easily calculate this proton affinity value using this Born-Haber cycle. I have chosen one example, a formation of ammonium chloride, where the proton affinity of ammonia we can find from this Born-Haber cycle. We have constructed this type of Born-Haber cycle where nitrogen, hydrogen and chlorine react with each other to form ammonium chloride directly. This is the formation of ammonium chloride, and here nitrogen and hydrogen react with each other in the stoichiometric ratio to form ammonia. This is the formation of ammonia, and remaining hydrogen and chlorine is there. Now this hydrogen get dissociated to hydrogen gas in atomic state, and this hydrogen atom get dissociated, get ionized, releasing one electron in a gaseous phase, applying ionization energy 1, producing H plus in gaseous state, that means proton in gaseous state. Here also chloride, molecule to chloride atom is produced in gaseous state. Now ammonia and this H plus ion both in gaseous state are react with each other or combine with each other to form NH4 plus, and in this state, in this process, the energy term is associated is called the proton affinity. This is delta H PA, proton affinity of ammonia. Now we can complete the cycle as like this. This ammonium plus and this chlorine atom in gaseous phase accepting one electron from outside to producing Cl minus, which is nothing but electron affinity in terms of energy, and this NH4 plus in gaseous state and chloride in gaseous state, both are combined with each other to form ammonium chloride again and complete the cycle. And since both this ion in gaseous state combine with solid to produce a solid, this step is called the lattice energy, lattice enthalpy of ammonium chloride. So applying this Hess's law like this as previous, we can easily calculate the proton affinity of ammonia like this. This is nothing but very high value, minus 886. So this value corresponds to the basicity in gaseous phase of ammonia. Now next application of Born-Haber cycle, it is very interesting. Here the formation or the existence of noble gas compound like krypton, argon, helium, xenon, radon, this type of noble gas, its compound, whether they exist, whether they can be formed, we can predict or we can get idea applying Born-Haber cycle. Here, one of the renowned scientists, Neil Bartlett, he was working with platinum hexafluoride complex and try to synthesize different type of platinum fluoride complexes, and accidentally he synthesized this type of O2 plus platinum hexafluoride minus type of compound, and he could isolate this compound as well as he formulated this compound like this. After the discovery or invention of this compound, comparing with this formula of this compound, xenon compound may be synthesized or formulated comparing with this oxo platinum fluoride compound. Since there are some data regarding O2 plus as well as xenon like this, for the first ionization energy of O2 gas to O2 plus is nothing but plus 1167 kmol inverse, whereas xenon gas to xenon plus gas, it is also almost same 1170 kmol inverse, as well as the atomic radius or size of O2 plus and xenon plus gas is almost same. So comparing these two ions, this type of synthesis of xenon compound like O2 plus platinum hexafluoride, Neil Bartlett synthesized this type of compound of xenon, and the corresponding Born-Haber cycles are there here for O2 plus PtF6 minus Born-Haber cycle, from where we can get the electron affinity value as well as the formation energy value, both are negative. So very small, though it can be synthesized or isolated. Comparing with this Born-Haber cycle, we can construct the Born-Haber cycle of Xe plus PtF6 minus like this: xenon gas to xenon plus gas and PTF6 gas to PTF6 minus gas, applying this electron affinity and combining these two ions form Xe plus PTF6 minus solid. Here also both this type of gas combine with each other to form this type of compound. And applying all these thermodynamical data, since xenon plus and O2 plus are almost same and their lattice energy is also same or should be same, hence we can find the formation energy of Xe plus PTF6 minus compound. It is nothing but negative, thermodynamically negative, almost 150 to 160 kJ mole inverse. So this data provide information that xenon compound, which is nothing but very less reactive or inert type species, since they are called inert gas, now novel gas, this novel gas compound can be synthesized or stabilized since its formation energy is something negative value. So from BornHaber cycle we can conclude, or we can have trace of xenon compound comparing with O2 plus PTF6 minus. That's all for today's lecture. Many more applications on BornHaber cycle are in different books. Hope you can solve them easily, and also you have enjoyed the current lecture on application of BornHaber cycle. If you are interested on covalent bonding, VSEPR theory and shapes of covalent molecules, and also concept of equivalent and non-equivalent hybrid orbital, you may visit these videos whose link is provided in the description box. Thank you for watching.